Let us take a block which is connected to a fixed wall by a spring shown here, as shown here, and this position is the equilibrium position of the system, the block and the spring system. Now, let's say an external force pulls the block away from the wall towards the direction shown by this arrow, and it gets displaced by a distance x, and after that it's held by that force before it's being released. So now the force that pulls it in this direction is doing positive work, so the spring tries to pull it back to equilibrium position here. The spring is trying to pull it back to the original equilibrium position, and so the force exerted by the spring is negative. This is a negative force because it's opposite to the direction of displacement. Now let's calculate the work done by this force. Now work done can be calculated by integrating f dx over the start to the final position. The initial position is 0 and the final position, let's say, is displaced by xm. The mass is displaced by a distance xm. Then we take f dx for a small displacement, and we can integrate it from 0 all the way to the position xm. So this, according to Hooke's law, f is given by minus kx, where my k is the spring constant and it's negative because, as we know, it's opposite to the direction of displacement. So we replace f here by a negative kx dx. Now if we integrate this, we get minus k x square by 2, because the x, when you integrate it, becomes x square by 2, minus k is the constant, all the way from, we apply the limits 0 to xm. This becomes minus k xm square by 2. Now this is the work done by the spring. In the direction shown, the force is exerted towards the wall, and this is the work done by the spring. So, but if you observe at the equilibrium position, the potential energy here at the equilibrium position, the potential energy is 0. So when it's pulled all the way to position xm, the final position shown here, the entire energy gained is completely equal to the work done without the sign, because the sign is because of the force acting in the opposite direction. So the entire energy here at the extreme position xm is nothing but the potential energy, because there is no velocity and hence kinetic energy is 0. So the potential energy at that position when the block is at xm is nothing but kxm square by 2. And this is true because this is a closed loop, and according to law of conservation of mechanical energy, the energy is completely conserved in the system. So when the kinetic energy is 0, the entire energy is potential energy, and that happens at the extreme position. But when the block is released, it will have a velocity at equilibrium position, and at the equilibrium position the entire energy will be kinetic, because at equilibrium potential energy is 0 at the equilibrium position. Thank you.